Hello everyone, welcome to the fourth unit of the series on density functional theory. In the last unit, I talked about the fundamentals of DFT that includes many-body Schrödinger equations and approximations for DFT and Hartree and Hartree-Fock theories. DFT is the most applicable tool for the electronic structure calculations of materials and by far the most commonly used theory to describe materials' behavior. We have already discussed that many different approaches are behind DFT in its foundations, such as Hohenberg and Kohn theory and Hartree and Hartree-Fock theories. In this unit, we can move ahead to examine how practical density functional theory was implemented relying on Kohn-Sham theory, and we will talk about how quantum mechanics works and the heart of DFT. So in this unit, I'm going to talk about the heart of DFT, which is Kohn-Sham theory. So by listening to this unit, you will understand how DFT works for the quantitative predictions of electronic structures. As we know already, in the Born-Oppenheimer-Hamiltonian, we have a kinetic energy term. That is the first term in this equation. And electron-electron interaction is the second term, and the last term is the interaction of the electrons with the ions. Of course, we already know that, as we discussed earlier, that there is one more term related to the ionic-ionic interactions. But because it doesn't depend on the electronic wave function, and it's just a constant value, we don't need to worry about that. That's why we don't mention this interaction, ionic-ionic interaction, in the Born-Oppenheimer-Hamiltonian here. So the last term here, the interaction of the electrons with ions, we can consider this term as the sum of our electrons of an external potential that's a function of where the electrons are. Let me explain more. So as we know already, the ions in a system generate a potential energy surface on which the electrons live. By looking at this equation, the only term that depends on the type of the material and the ion positions in our system is the last term, the external potential. The first two terms here in this equation, kinetic energy term and electron interaction term, are completely general and don't depend at all on the type of our system and the ionic positions. But the last term, the electron-ion interaction term, depends on ionic position in our system. I mean is that if our system is iron or aluminum or whatever, the type of our system can affect only the last term. But the first two terms are general and don't depend at all on the specific materials. So all the information about the specific aspects of our system is in the external potential and is a function of 3 dimensions. Keep in mind that the wave function of the electrons live in 3 n-dimensional space, but now the potential in which the electrons live is in only 3-dimensional space. So generally, the way that quantum mechanics works is that we start with a 3-dimensional potential, which is called external potential. An external potential, that's a function of r, the electronic position, lives in 3-dimensional space. Then we will build a Hamiltonian with that external potential. Then we will obtain the wave function and energy of our system. But the wave function lives in 3n-dimensional space. Indeed, we start with the 3-dimensional external potential, then using Hamiltonian, we will obtain the wave function which lives in 3n-dimensional space and the energy. And from that, we can obtain any properties that we need of that material. Well, as we already know, Hohenberg and Kohn theory is a foundation of density functional theory that we are going to apply for electronic structure calculations. Based on this theory, the electron density has the fundamental and central role of the external potential in the way we have been doing quantum mechanics. is that the ground state electron density uniquely determines this external potential. So there is a unique correspondence between the three-dimensional external potential and the three-dimensional electron density. So we can say that the ground state electron density governs and determines the wave function and then the energy of the system, and from there we can calculate the properties. So based on the Hohenberg-Kohn theory, ground state electron density governs the external potential, and by having the external potential we can obtain the wave function and the energy and then the properties of the system. It's very interesting that everything depends on the electron density. Then all we need to do is finding a three-dimensional electron density and not a three-n-dimensional wave function. So we would avoid the challenge of 3n dimensionality problem, and we should be able to solve these equations in a reasonable amount of computational time. To sum up, based on the Hohenberg-Kohn theory, the ground state wave function is a function of the ground state electron density. So if we know the ground state electron density as a function of position, we can in principle obtain the three-dimensional full wave. That the ground state energy is a function of the ground state density. So if we know the ground state electron density, in principle the ground state energy is a function of this density. It's interesting that we can say that if we can write this energy functional of the electron density, then we can find the electron density that minimizes the energy functional. It means that the ground state electron density will give an energy that's lower than the energy given by any other electron density in that system. Well, now the challenge is that we don't know what is functional exactly, but we know that there is a function, but we don't know what does it look like. So Kohn-Sham approach proposes an applicable way for solving this DFT problem, and we are going to describe very briefly. So just to summarize the problem is regarding the finding of the energy function. The solution is exact so far, but the energy is a functional of the electron density that we don't know that functional. This is a problem that we don't know that functional. So what Kohn-Sham did is they took the idea of the single electron orbitals and the system of non-interacting electrons where the ground state density is the same as the real system and the positions of the ions are the same in both systems. So we assume that each electron moves independently in a potential created by the ions and the rest of the electrons. What we are going to do is write in the energy terms of a simple functional that we know, plus we are going to write everything that we don't know about the correlations and about exchange into one function. So let's do the following. We know that the energy is a combination of kinetic energy, electron interaction, as we know it is called the Hartree term, which is exact, and ion-electron interaction, external potential in a mean field kind of way, and exchange correlation energy, which is sort of everything. Let's start with the first term, that is the kinetic energy. So Kohn-Sham proposed a non-interacting kinetic energy, and the reason is simple. And now if we write the electron density as a product of orbital densities, we will be able to obtain the kinetic energy of the non-interacting system from those orbitals. It would just be the sum of all the one-electron kinetic energies associated with those orbitals. It's the non-interacting kinetic energy of a single particle system. There is also an external potential which is associated with the electron-ion interactions. That's pretty easy to deal with this external potential, and we already know the exact solution for that. For the electron-electron interaction, what Kohn-Sham did was that they wrote it as a sum of something that we know how to write plus corrections that we don't know exactly. The part that we know how to write is a Hartree term. If you remember from Hartree, electron-electron interaction is done in a mean field kind of way, so that's a functional also of the electron density from these orbitals. That is why we call it the UH here, the Hartree potential. That's a classical electron-electron interaction without any exchange and correlation. For the real system, we have an extra term, that is the exchange and correlation contribution to the electron-electron interaction. That if you remember, Hartree assumes a simple product of orbitals, no exchange and no correlations. So everything that's more complicated are moved into this function, exchange correlation function. So it looks just rearranging the terms and putting everything that's unknown and we don't know about that into a single term that is called exchange and correlation function. By looking at this energy expression, we can clearly see that Kohn-Sham equation is exactly like a Hartree equation, but the only difference is that in Kohn-Sham equations, we have external potential plus exchange correlation function instead of having only external potential in Hartree equation. So only the last term, exchange and correlation function, is added to the Hartree equation. And if we take the Hartree equation and replace external potential with external potential plus exchange correlation function, then we have these Kohn-Sham equations. We know the exact solution for the Hartree equation, so we can use that to solve the Kohn-Sham equations. That's the trick, is to move everything we don't know into one term that looks like an effective external potential. There is still one challenge, that we need appropriate approximations for that exchange correlation potential. So there are still some challenges that we will briefly discuss in the rest of this unit and more comprehensively in the next units. The first one is how we approximate this exchange and correlation function in a proper way that is more close to the exact solution. The next one is associated with some few numerical issues that we have to be aware of that when working with DFT. We are going to use a basis set, a set of functions to describe these Kohn-Sham orbitals that affects the accuracy of our calculations, and these basis sets could be plane waves or could be localized basis sets. And also we use pseudopotentials to replace core electrons. Most of the time when we do DFT calculations, not always, we replace the electrons that are near the core with what's called a pseudopotential that takes care, because those electrons that are low energy electrons are very inert, and we know that they don't participate in bonding. So we put them, the electrons are close to the core, we put them in the potential and make sure that the outermost electrons see these electrons in the appropriate way. Those are called pseudopotentials that DFT codes typically provide a library of potentials for different elements. So let's talk briefly about exchange and correlation functions in this unit to get to know the general concept of that, and we will discuss it with more details in the next units. So generally, the exchange and correlation functional is a function of the electron density that gives us all the contribution of the exchange and correlation to the total energy. Well, there is two exchange correlation functionals that we mostly use today in our DFT calculations. There are, of course, more exchange and correlation functions, but here in this unit, I will introduce to you the most two important ones. The first one is called local density approximations, LDA. This exchange correlation functional is simply an integral over a space of a function that depends only on the local density at that point. LDA consider the exchange and correlation terms by two different terms, the exchange term and the correlation term. For the exchange term, there is an exact equation for homogeneous non-interacting electron gas, and we have an analytical solution for that. For homogeneous system, the exchange energy can be written as the density to power 4 thirds. What we assume is that the exchange part of the exchange correlation potential is an integral over all the space of that local density at that point to power 4 thirds. So this works for the homogeneous gas with no gradients. So this ignores any sort of effect of gradients and variations in the density. And as long as density doesn't abruptly change in a space, this exchange correlation works very well. That's the exchange part. But for the correlation part, there is no analytical solution. But Euler in 1980 performed very expensive quantum Monte Carlo simulations and obtained numerical values for this correlation, also for the homogeneous gas, that can be used in our DFT calculations. So, well, LDA has serious limitations for energies, although it gives accurate geometries. So we'll try to improve our functionals by making them dependent on the degree to which the density is locally changing, which is the gradient. So if I have dependence on both the density and the gradient of the density, I call that the gradient corrected or a generalized gradient approximation functional, which is GGA. So I will talk about the next exchange correlation functional that is called GGA that consider both the density and the gradient of the density. So GGA is a generalized gradient approximation, and here the exchange and correlation functional depends on the local density. It's an integral over the space of some function, just like LDA, plus a function of the gradient of the density. So GGA exchange correlation function consider both the electron density and the gradient of the electron density. So there is gradient corrections that account for variations of the densities, and these GGA functionals work a little bit better than LDA, especially for things like defects and where you would expect because there is larger variations of electron density. There are different parameterizations, and the most popular one is called PBE from 1996, but there are others like BLYP and B3LYP. Hyper-GGA, like B3LYP, is a mix little bit of GGA, for example 30% of exact exchange Hartree-Fock, and as we already know, in Hartree-Fock we describe exchange exactly. So using B3LYP in our DFT calculations leads to improve the accuracy of our calculations, but we need to take into account that B3LYP, because it's using the exact exchange of Hartree-Fock theories, it's more expensive computationally. So in the case that we cannot get the right properties in our DFT calculations, sometimes we need to use a hyper GGA like B3LYP, especially for the calculation of the band structures and the electronic properties of some materials. All in all, for this unit, Kohn-Sham equation, that is the heart of DFT, must be solved in self-consistency. So that first we have an initial electron density, initial guess of electron density for our system. And then we have to calculate the effective potential and put it into our Hamiltonian to solve the Kohn-Sham equations. Then we obtain a set of wave functions to calculate new electron density for our system. If the electron density we got here is the same as the one we had as the initial guess, then we have self-consistency in our loop. Then we can calculate the ground state energy and other properties of our systems. But if the electron density here is not the same as the initial one, then we replace the calculated electron density as the new trial and then just loop through again, and so that's how we can find the lowest ground state energy and electron density and other properties through DFT calculations. So in this unit we talk about DFT in a very general way, and if you are interested in learning more, there are many resources, many other books and papers, and I would like to introduce to you two of the best ones to my opinion. I would recommend this paper, which is very useful and very general. In addition, I would like to recommend the other reference, that is the ABC of DFT, which is a freely available online resource that is very useful. I put the link below to download this resource for the ones are interested in. So you know that there are a variety of simulation tools for density functional theory, but here I would like to talk about the most popular one, WASP, Vienna Ab Initio simulation package, and different things that would be helpful for DFT calculations. And I will try to cover many aspects such as applying different exchange correlation functions, charge analysis, bond strength calculations, phonon calculations, and many more, and share my experiences in the next videos. So please subscribe to this channel and hit the bell icon to be notified the next videos, and thank you very much for listening.